Welcome back to Chem Help ASAP. We have our orbital energy diagram, and now it's time to put electrons in it. If you want to review how to construct the orbital diagram using quantum numbers, please feel free to check out my previous video. But let's start placing electrons.
Now, as we put electrons in, there are three rules that we need to keep in mind. Rule number one is based on the Aufbau principle. And all that says is start with your lowest energy orbital. So we're going to start from the bottom of our energy diagram. Rule number two is the Pauli exclusion principle. And this states that each orbital is going to hold 2 electrons. However, they must be spin up and spin down. So if you remember again from our previous video, we talked about each electron has a unique set of quantum numbers. So we cannot have 2 electrons in one orbital that are, say, both spin up or both spin down. They are going to be opposite. Our third rule is Hund's rule. Hund's rule is going to become important when we have our degenerate orbitals, and what we need to do is we need to keep electrons unpaired if possible in those degenerate orbitals. This is going to make a lot more sense once we start putting electrons in. So we're going to start with our simplest element. We're going to start with hydrogen. Now, how many electrons does hydrogen have? Hydrogen has 1 electron. We are going to obey all 3 rules for this. We need to start at the bottom. So I'm going to start in the 1s orbital. I'm going to make that electron spin up. I just always start with the spin up arrow. And we have obeyed all 3 of these rules. We have not put more than 2 electrons in an orbital, and this electron is unpaired. So hydrogen's 1 electron is going to be found in the 1s orbital. Now let's talk about helium. Helium has 2 electrons. Still going to obey our 3 rules, except now we're going to add a second electron to that 1s orbital. Again, you'll notice I put it as spin down because I'm following the Pauli exclusion principle. Now you might say, why didn't you do Hund's rule? Why not put that extra electron in the 2s? And I didn't because the 1s and 2s orbitals are not degenerate. They don't have the same energy. Let's move on to lithium. Lithium has 3 electrons. The first 2, of course, go in the 1s. The third electron goes in my 2s orbital. Hopefully you're starting to see a pattern here. Let's move on to beryllium. Beryllium has 4 electrons. Again, if I'm going to add 1 more here, I'm going to add it to the 2s orbital. Okay, so now I have the 1s and the 2s orbital filled. When I move on to boron, which has 5 electrons, I'm going to start filling the 2p. So this is boron with its 5 electrons. Okay, let's keep going. Carbon has 6 electrons. Now this is where Hund's rule comes into play, because that 6th electron, initially you might want to pair it up with that electron there and say the 2px orbital. However, Hund's rule states that we're going to keep electrons unpaired as much as possible. So let's erase our arrow there. And we are actually going to put this electron in another 2p orbital. So this way we have 2 unpaired electrons. Let's keep going. Nitrogen has 7 electrons. Again, we want to keep these unpaired as much as possible. So I'm going to put that 7th electron in what would be the 2pz orbital. If I move on to oxygen, now I have 8 electrons. Okay. I cannot put my 8th electron in the 3s yet because Aufbau principle tells me that I need to fill electrons from the lowest energy. I still have slots available in a lower energy orbital. So I'm going to erase this electron, and this electron needs to now be paired. So now I have only 2 unpaired electrons in those 2p orbitals. So at this point, again, you can predict what's going to happen. Fluorine has 9 electrons. I'm going to pair up This p orbital, and neon has 10 electrons. And we finish pairing up in the 2p orbital, which means that when we move to sodium with 11 electrons, now we can finally move to the 3s orbital. This is very much like filling an apartment building. You're going to fill from the ground floor first, and as much as possible, you're going to give people their own rooms. However, you're not going to start filling a higher floor until your lowest floors are filled. So in essence, we had to wait until our second floor was filled before we started filling the third floor. Let's switch to a fresh energy diagram. Okay, let's do an element with more than 5 electrons. Let's do phosphorus. Phosphorus has 15 electrons. Of course, I'm going to start in the 1s, and I'm just going to fill this energy diagram until I reach 15 electrons. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is the energy diagram for phosphorus. Notice when I got to the 3 P's, I kept things unpaired as much as possible. So phosphorus has 3 unpaired electrons in the 3p. Let's clear this diagram and do another element. Okay, let's do calcium. Calcium has 20 electrons. Okay, so I'm just going to start filling. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I just fill to the 4s. Let's jump quickly to scandium. Scandium has 21 electrons. And you'll notice here that after the 4s, my next lowest orbital is the 3d. So this one extra electron here for scandium gets put in the 3d orbital. Let's add some more d electrons in. Let's switch over to iron. Iron has 26 electrons. Okay, so my diagram right now has 21. So I'll go 22, 23, 24, 25, and then 26 I will have to pair. Again, the D's are working just like the P's. I'm going to keep things unpaired as much as possible until I max out my unpaired, and then I'll go back and start pairing them up again. Let's clear my diagram one more time and fill one more energy diagram. My last example that I'm going to do in this video is barium. Barium has 56 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, almost there. 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56. So barium, with its 56 electrons, happens to max out my energy diagram. However, you can draw this energy diagram for any element in the periodic table. If you're going to go past 56 electrons, you just need to start including the other orbitals. Using the orbital energy diagram is super helpful in understanding why some orbitals get filled before others and being able to see which orbitals are degenerate very clearly. However, it starts to get cumbersome if we're trying to compare multiple elements. So in our next video, we are going to use a much simpler and much more compact way to specify exactly where our electrons are in each element. I hope you found this helpful, and thanks for watching.